Alright, welcome back. This is video 2. We're going to be taking a look at forward passes and implementing activation functions in our forward passes in Python. So we'll be doing everything through code. So we're going to be going over a basic Python review today and then looking at modeling whatever math we did last video in our code. So Alright, so we have four things to model or to represent when modeling a single neuron, right? Before we even talk about those four things, let's go look at what we're actually modeling. So this image, pretty much, this single neuron is what we're going to be modeling. And remember how we talked about how this neuron by itself is almost the same as this image as well? So that's what we're going to be modeling. We're going to be modeling this single neuron, not the layer or not the entire neural network, just this one neuron. And then we'll build our way up from there, and then we'll learn how to model these layers at a time, which we call batches when we're modeling those. So we'll be learning how to make the entire neural network eventually, but for now we'll be focusing on modeling this one tiny neuron right here. And like we discussed earlier in the previous video, we have four things that really tell us or really define what a neuron is, right? We have the inputs coming into the neuron. We have the weights per connection coming into the neuron. And remember, the number of inputs coming in and the number of weights you have per neuron have to be the same, as we discussed earlier, because every single neuron in one layer has a connection into every neuron in the previous layer. So that should make some amount of sense. We also have the bias for the neuron, and there's only going to be one bias per neuron. So when we're modeling this one neuron, we'll only have one bias. But if we were to model this entire layer right here, we would have four biases because there's four neurons. And just as how we would have four biases, we'd also have 16 weights because, oh, not 16, I'm sorry, 12 weights because there's three connections per neuron. So that means because there's four neurons, we'll have 12 connections total for this entire layer. So that's just something to think about for now. And finally, we also have to represent the outputs, right? So those four things are the main things we're gonna really represent real quick in our code, and then we'll get to actually working with them and programming some math so that we get a desired output for this neuron. So we can start off with the inputs. And like we saw earlier, the inputs into a neuron, right? It doesn't have to be a finite number of inputs. As we looked at in this image, for this neuron, there's 1, 2 inputs. For this neuron, there's 1, 2, 3 inputs. So there is no set amount of inputs you can have into a neuron. It's simply dependent on however many neurons are in the layer behind it. So if you were looking at the inputs into this neuron, you'd have 4 coming from every single neuron in the layer behind it. So the inputs have to be represented by something that is dynamic. It can't be just set to one value because there could be more than one input, right? So whenever doing that in code, we will create an array or a list in Python. That's what we call them, a list. And this list, we can just initialize to be anything for now. So let's say our inputs for this one neuron that we're going to make is going to be 0, -1, 2, and 3. So we have 4 inputs coming into the neuron. And like a visual representation of what that would look like would be just this neuron right here. So what we just did is turn this little chunk right here for this one neuron into code. And this 0, -1, 2, and 3, they all respectively belong to these neurons, and they're just going to send them to that one neuron in the final layer, right? So yeah, that's pretty much what our inputs are going to be. And to model our outputs, or output, we'll also have to create a variable, right? But for this situation, our output doesn't have to be a list necessarily, right? Because we discussed earlier that the output for a neuron is going to be the same no matter where you're sending it, right? So if all of these values are 18, we don't really have to go through the trouble of creating a list just to represent all these connections. We can just say that the output is 18. So our output, we haven't decided what it is yet, but our output we can initialize to be 0. And that is pretty much this is only that's pretty much what we're going to be doing for now. And this is only the case for a single neuron, by the way, because think about it. If we were to model this entire layer, we would have 4 outputs, right? Because we have 4 neurons that are sending 4 individual outputs to a different neuron in the layer in front of it, right? So if we were to model this entire layer, not just this one neuron, we would have 4 outputs. But because we're modeling just this one neuron, we only have 1 output. Okay. We also have the weights, so we can write the weights is equal to, and we also have the bias. Bias is equal to. The bias is going to be the same for the entire neuron as we discussed, so we can just set that to be 3. But the weights, on the other hand, are dependent on however many neurons are in the layer behind it, right? And in this case, the layer behind it is simply going to be the inputs. So this is pretty much, we're basically modeling a neuron in the first hidden layer of a neural network. So the layer behind it is going to be inputs. So that means the weights are going to be dependent on however many elements are in this list. So because we have 1, 2, 3, 4 elements, we'll have to have 4 values for our weight connections in order for this to actually work properly. So we can make our weights 0.5, negative 1.5, 2, and then 1. So these could be our weights, right? And if you're following along at home, make sure to use exactly the same numbers just to make sure you get the right values at the end, because we'll be doing a little bit of math. And if you use different numbers, you won't be able to know if anything went wrong in the code, because there'll probably be a unique set of numbers that no one's ever done before. So if you want to just check to see if you've done it right, you can use the same exact numbers I'm using. Okay, and so we've represented these 4 values for our neuron, right? So now we can start looking at some of the math that we did earlier. Alright, so let's take a look at some of the math that we went over in the video before we even start modeling it in programming, right? Just so we can give ourselves a refresher and go back to it. Alright, so our final equation for the output of a single neuron ended up being the sum of the weights times the inputs plus the bias. So that's just the sum of whatever the input is, which would be 4 right here, times the weight of the respective connection, which is 0.5. And you do the same for all of the inputs and the weights respectively, right? And so down here, I made a tiny little neural network that models exactly what we've written out in our code so far, right? It has 4 inputs, one bias, and 1 output. So this is pretty much exactly what we have coded so far, and this is the output. So we're trying to solve. Okay, so looking at our weights and biases, right? I've labeled the inputs kind of in order of the element location, right? So from top to bottom, it starts from element 0 going to element 3, and that element 0 will be 0 right over here, and element 3 will be 3. And if you're wondering as to why I'm counting from 0, in programming, whenever you're counting or starting off something, you always start from index 0, and then you start going up. You don't start from 1 like you would normally do. So this would be 0, 1, 2, 3. All right, so this is the 3rd location in the list, because we start from 0. And I put these weights with their respective element and inputs. So this is element 0 or index 0, and this is index 0 as well. This is index 1, this is index 1, this is index 2, this is index 2, this is index 3, this is index 3. So these are paired based on what index they are in the list. And the bias is just the same for the entire neuron, so it just applies to all of it. And we're solving for the output, right? So when we're trying to model this, write out the output is equal to, we just talked about how it was a sum of the weights and biases, so when doing that in code, we'll have to specify which weights and biases you're talking about because the computer doesn't really know. So we'll do it. Weights. So what is this, right? It's basically saying we're taking the 0th index from the inputs list and multiplying it by the weights, the 0th index, sorry, in the weights list. So we have 0, pretty much this is the inputs 0. This is what we're getting when we run this. We get 0 times weights 0, which is pretty much this. So we get 0 times 0.5, and that's pretty much it. And remember, it's the sum of all weights and biases, right? So we can't just multiply these two and go about our day. We have to multiply these two, and these two as well, and then sum all that together. So why don't we get to copy pasting, right? Oh, we have to add. I didn't even copy this. Hold up. There we go. What am I typing, man? Okay, so this should also look pretty familiar. It's just doing the same exact thing, but for the first index. So these two values. So this would be a -1 from index 1. This would be a -1.5 from weights 1. And then we do it again. Add a plus, Control V, and then 2. And one more time. Let me make this a little bit wider. Alright, so this is our this is basically just this part of our equation right here. So this we have modeled already now. And you can already kind of see why doing the math this way is kind of like tedious and unnecessary because neural networks aren't limited to 4 inputs or 5 inputs or 6 or 1,000 or 10,000. They're not limited by anything pretty much. So you could have 10 million inputs. And imagine trying to do this, individually writing out however many inputs there are versus however many weight connections there are. It would be impossible, like genuinely impossible. So we don't really do it like this, but visually, like just a concept for our conceptual purposes and just to understand how it works fundamentally, this is pretty much what it would look like if you were doing it by like the long way. Alright, so if we print the output, we should be getting a number around 11.5, or we should be getting 11.5, right? As I went ahead and did the math really quickly, I put everything in the calculator, I plugged and chugged, and we got 11.5. So if I run this, we should get 11.5. Oh, you see the 11.5 up here? Alright, yeah, we get 11.5, so this model is pretty accurate, and it worked well. But it looks like pretty clunky, right? It looks pretty big, tedious, and lengthy. We don't like this representation, right? We don't like this mathematical representation. Because if we had a neural network with 100 inputs, or 1,000 inputs, or 10,000 inputs, right? This would get very big, very, very fast. And because there's like no limitation to however many inputs or weights you have in a neural network, this is never a good way to model it mathematically. So we want to find a shorthand way of representing this, right? We want to find a shorthand way of representing the sum of all the inputs and the weights time multiplied together, right? The sum of all the inputs and weights respectively multiplied by together, right? So how can we do that, right? There's lucky for us, there's a very, very useful mathematical equation, right? It's called the dot product. And we can use the dot product to pretty much replace all of this with like one line of code, like a very, very simple line of code. And before we do that, why don't we go ahead and discuss what the dot product actually is, right? So the dot product. I'm gonna start off with a big equation. It might look a little confusing for now, but we'll break it down. The dot product, or A dot B, is equivalent to the sum from I equals 1 to I equals n of AI times BI. And this should look very familiar to you. And it should look familiar to you because it's exactly this. It looks exactly like the sum of the weights to the sum of the weights times inputs, right? It looks exactly the same. And that is because it is exactly the same. What we've been doing all along is basically taking the dot product. But in normal Python, right? It doesn't allow us to just take the dot product. There is no command or function or anything like that to take the dot product. So we'll have to use an external math library in Python. It is one of the most popular and most widely used libraries in Python. It's called NumPy. So we'll have to import NumPy and then we can start using the dot product. But um, we had to go over what a dot product actually was beforehand, right? And just to go over it one more time to clear up any more confusion if there is any remaining. If we had an array or a list with -1, 2, and 3 in it, and this could be our inputs, and we also had an array with 3, 0, -1 in it, these could be our weights for each respective input. If we took the dot product of I dot W, our result would be -1 times 3 plus 2 times 0 plus 3 times -1. Oh, times -1. Okay, so we get -3 plus 0 minus 3. So -6, right? This would be our output. And it's interesting because this is literally exactly what we've done. So there's no change, there's nothing, you don't have to really do anything with the indexes. It's literally exactly what we've done so far. But instead of writing it out in this big clunky way in which we'd have to write out the sum every single time, we're gonna rewrite it as a dot b. And hopefully once I start programming it, it'll make a little bit more sense to you if you're confused right now, but alright, so before we start, I mentioned how we had to import a math library. So we can go ahead and do that now. It's called NumPy. And we'll be importing that real quick. And now we can start rewriting this big equation into a better, more concise version. So we can do output is still equal to, we'll call the NumPy function, we'll call NumPy, we'll call the dot product from NumPy by doing np dot dot, sorry. And what are the two things we're trying to dot together? Remember how a dot b is equal to the sum of ai times bi? Isn't that just the same as saying inputs dot weights is equal to the sum of inputs times weights, which is exactly what we're trying to do? So if it's asking us for the a and b values, we can just give it the entire list. We can give it inputs and we can give it weights. And remember how we had to specify which value it was in inputs and which value it was in weights by saying it's the 0th index or the first index, right? We don't have to do that for the dot product because the whole point of the dot product is to go through the entire array or list. So it already knows from the start that it's going to have to do it for every single index. So it's built into the dot product, which is very cool and useful. That's why it makes it such a shorthand method of doing it, right? And then we add the bias to the end and we're done. So it went from this big clunky equation right here to this tiny equation down here. And this equation will never change. It'll always remain the same. This one could get bigger and smaller depending on how many inputs you have, right? Because you could have inputs going up to index 50 or 60 or something like that. And your equation will get super massive. But this one will stay the same size. So if we were to get rid of this and then run it again, we should still get 11.5, which we do. So it does work. And yeah, so because it works, we can just replace that big clunky equation with this now. Alright, so what if we wanted to model more than one neuron, right? What if we wanted to model like an entire batch or hidden layer or a layer at all, right? So what we've programmed so far is just some code to try to find the output for a single neuron, right? And visually speaking, this is what we're looking at. This is what we programmed, right? We programmed to solve for this output. Now, why don't we try solving for multiple outputs coming out of these two neurons respectively, right? So instead of solving for this output right here, we'd be solving for these two outputs. So output 1, output 2, right? And so basically what we're going to be learning is how to model neurons in layers now, not just by individual neurons. So uh, this is applicable to any number of neurons in a layer, so not just two. So after we learn how to do two, we can start doing it with 4 neurons, 7 neurons, 8 neurons, 10 neurons, or however many neurons you'd like. So before we even start, why don't we talk about some of the differences between modeling a single neuron and a layer, right? So what would really change when modeling this stuff? So to the right, let's write down the stuff that we actually represented in our code. So earlier we represented the inputs for a layer. We represented the outputs. We represented the biases, and we represented the weights, right? And we can start comparing what the inputs we can start comparing these values to what they look like individually modeling it and modeling it as a layer, right? So if we take a look at the inputs, so let's say that our inputs were -2, 1, 0, and 3, right? Those are our inputs for this hidden layer right here. And how do we know those are the inputs to this hidden layer right here? It's because those are the outputs of the layer behind it. So those are the inputs coming into this layer, right? Will the number of inputs change if I get rid of this neuron right here, right? Will the number of inputs change? No, right? There's still going to be 4 inputs coming into this layer, right? It doesn't change how many inputs are in the layer behind it because you're not doing nothing to that, right? So the number of inputs do not change, right? Will the number of outputs change when comparing this to the individual neuron, right? Will the number of outputs change if I uh if I got rid of this second neuron? Will the number of outputs change? Well, yes, because you're getting rid of this entire output over here. So yes, the number of outputs would change. Um, so that means the outputs change when modeling an entire layer, and these don't change. That's a terrible line. Okay, whatever. Um, sorry. Will the number of biases change if I get rid of this neuron right here? Yes, because we're getting rid of an entire neuron by itself, right? So whatever bias this neuron had is just gone. So this would change. What about the weights? If we got rid of this entire neuron right here, what would happen to the weights? Well, because the weights are respective to the connections between neurons, you're getting rid of this connection between the -2 and this neuron right here, this connection right here. You're getting rid of that. You're getting rid of this, and you're getting rid of this, and you're getting rid of this, right? You're getting rid of 4 connections, which in turn means you're getting rid of 4 weights if you get rid of this neuron. So the weights do change depending on how many neurons you have in the layer. So the only thing that doesn't change is the inputs. Everything else will be changing. So why don't we try representing that in our code, right? How can we represent that in our code? So far we have our inputs being this right here, right? And our outputs being this. We know that our outputs can't be one value anymore because we're not modeling one output. We have multiple outputs. We have 2 in this case, right? We have 2 in this scenario. So we'll have to make a list as well for the outputs just so we can hold more than one value. So we'll change outputs value to a list, not initialized to anything yet. We can maybe do 0, 0 if we wanted, but it's initialized to nothing for now. Our weights would also have to change, and we can represent more weights in this model, right? By simply treating these 4 values, right, as an individual element. And what do I mean by that? I mean we're going to be treating these 4 connections that lead into this one neuron right here. This is called neuron 1. It's called neuron 2. So these 4 inputs coming into neuron 1 we'll be treating as one value. And then we'll be treating the 4 inputs going into neuron 2 as one value as well. And what do I mean by that? So if we wanted to represent more than one weight, right? Because we know that the inputs are all going to remain the same, so we don't really have to change these. Because these inputs are going to be the same going into both neurons. They're going to be 0, -1, 2, and 3. Nothing's going to change. But our weights, right? We're going to have more of them because we have an extra neuron. So how do we represent that? So if these four numbers right here, right, is our representation of one neuron, why don't we just make another list that includes this a smaller list inside of it, right? And just call it a day like that. Why don't we just do that? So we turn to this 1D array or 1D list, one dimension list, into a two-dimensional list with a list inside of it, right? So you can do this in programming. It's like a pretty common concept. You can even have 3D arrays in which you have a list inside of a list inside of a list. So if you're a little confused as to like the actual coding, the formatting, and why uh I'm or why or how I'm getting all these like functions and like how I know what like brackets to use and stuff like that. You should always just take a look at some of the learning resources I've provided as they'll go over some of these concepts so that it'll be easier to follow. So let's fill this with a random weight values. So for a second neuron, we can say that it has weights of 2, -1, 0, and 1.5. Okay, why don't we say that? So these four weights are respective to, let's see, they're respective to this, right? So 1, 2, 3, 4. Those all correspond to these numbers right here, right? These numbers, on the other hand, they correspond to this, 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 and this going into the second neuron. So that's pretty much how we're defining the weights for our neurons right now. We're creating a 2D array with two elements in it, two element lists in it with four elements inside those lists. So there's one element right here, another element right here. So there's two elements in the big list, and then there's four tiny elements in the two lists right here. So yeah, so we're simply creating a 2x4 2D array. And we can actually go ahead and create a matrix, which is what a 2D array is called, and visually show what that would look like, right? So if I pull up my thing and just drag it to the side real quick, go ahead and pull this open. So we have 0, -1. Oh, those are inputs, never mind. We have 0.5, -1.5, 2 and 1. Now we have 2, -1, 0, and 1.5. So these are, this is what basically our 2D array looks like visually that we just programmed, right? And come back to this. So this is what I'm talking about when I mention say 2D array, this right here. So this is what it would look like as a matrix. And this top row right here, these rows on the side, these rows tell us what neuron it is pretty much, right? So this is the first neuron, it's the first row. This is the second neuron because it's the second row. These columns right here, right? These 1, 2, 3, 4 columns right here, right? These tell us what the weight is in that respective column, right? They don't really have any important meaning, right? But these are just the columns in which the weights are in, right? And understanding really the relationship between what the columns and weights are is very important when doing dot products, and we'll be talking about this later and why it's such an important detail later, right? When we start talking about transposing these matrices to make the dot product actually work, and we'll be going over exactly what all of this is later, but I just want to show you guys what this 2D array would kind of look like and visually speaking, you know, and basically the more let's say we added a third neuron. So we added a third array inside of this big one, the third list inside of this big list right here, right? If we did that, all we would do is just add another row because the rows equate to neurons, right? So we just add another row and have the 4 values in there as well. So that's pretty much how this matrix works. So yeah, that's why we use matrices when modeling more than one neuron, right? Because it allows us to add another variable pretty much, right? So that's why they're useful. So this is our 2D array for both neurons. So the weights. All right. So before we continue, I wanted to clarify a couple things. So we have weights equal to this 2D array that we made, right? And in which this tiny array in the zeroth index of the big array, right? These 4 numbers right here, they represent one neuron, and these 4 numbers right here, they represent another neuron. And they represent the weights per connection going into the neuron. So uh it would be good to better clarify what the weights is actually equal to. So we're gonna rename this weights layer, and then these are the biases for that layer, right? So we have 2 neurons in the layer, so we have 1, 2, so we have 2 biases. So we'll name this biases layer as well, and we should be good. All right, so now we can start using NumPy functions, right? That's the whole point of importing NumPy. Before we do that, there's one thing we have to do. NumPy works with these lists, these what we would call lists in Python, right? It works with those, but we call them NumPy arrays. And NumPy arrays are pretty much exactly the same thing, but the arrays work better with the functions in NumPy, so you can use more NumPy functions on the arrays. So if you try to do a couple like if you were trying to do certain things to this Python list using NumPy, you wouldn't be able to do it unless you convert it into an array. So we'll start off by creating or reassigning the value of inputs to be np.array of inputs. Oh, missed that. Okay. That should work perfect, yeah. Alright, and we'll also be doing the same for the weights as well, because we're going to be using the np dot function on the weights and the inputs, so we'll be recreating the weights. So weights layer is equal to np dot array of weights layer. Alright, so now that we have 2 NumPy arrays that we can work with, we can rewrite the equation that we got earlier, the really lengthy one. We can go ahead and rewrite that as output is equal to np dot. So this is the function that you'd use. This is np dot, and we'll put in our a and b values, which will be our inputs and our weights layer, and then we will add our bias to the total. Oh, it's not called biases anymore though, it's called biases layer. Okay. Alright, so if we run this code, we get a dimension error, right? So it's letting us know that our shapes 4, nothing, and our shapes 2, 4 are not aligned, which means that the dimension 0th, or the 0th index of the 0th dimension, is not equal to the 0th dimension for the second object. So what does this mean, right? So it's talking about shapes 4, nothing. What does that really mean? So when it's saying this, it's referring to this input right here, right? And we know that because it's saying the shape is 4, nothing. And with arrays, the shape is pretty much it's determined by how many elements you have in that 1D array, right? So just for 1D arrays, the shape is determined by how many elements you have in that array. So in this array, we have 1, 2, 3, 4. We have 4 elements, so the shape is going to be 4, nothing. And for the second object, so for our weights layer, we have 2, 4. And what does it mean by 2, 4, right? So it's basically saying that it has 2 rows and 4 columns. And this is pretty much the same array, right? But in matrix format, so you guys can easily see the rows and the columns. But so it's basically saying with a shape of 2 comma 4, there are 2 rows, so 1 row here, 1 row here, and 4 columns. So 1, 2, 3, 4, 4 columns. And in our code, that would look like um, smaller arrays nestled into a bigger array, right? So we have 1 row right here, and another row right here, and the columns would be these weight values inside the rows, right? So this would be a column 0.5, negative 1.5, 2, and 1, and this would be a column below that, so it'd be 2, negative 1, 0, 1.5. So that's basically how shapes work with arrays, and it's basically letting us know that there is an error that exists because the dimension 0, or whatever the dimension for this object is, right? So dimension 0 would be 4, is not equal to the dimension 0 of the second object, right? So that which would be 2. So the dimension 0 for the second object would be 2. And because 4 does not equal 2, we're getting an error. So what does that mean? It pretty much leads us to conclude that there's like a certain relationship that two arrays need to have when you dot them together. The first number for the shape has to correspond and equal the first number for the second shape. So if 4 does not equal whatever this value is, it won't be able to work properly. And this should make sense if you look at it visually, right? So if we come over here, and then we recreate the input layer, or the input values real quick, we had 0, negative 1, 2, and 3. So 0, negative 1, 2, and 3, right? So say we're trying to dot these two things together, right? So how would that work? Alright, so when dotting a one-dimensional array with a matrix, right? There's a different set of rules we kind of follow. We don't go by kind of like row. So we don't do 0 times 0.5 plus negative 1 times negative 1.5, 2 times 2. We don't do that. We go from this row multiplied into the column. So what we would have is 0.5 times 0, negative 1 times 2, and then, oh, we come up empty-handed, right? Because there's only 2 values in this column, but 4 values in this row. And that is exactly why this computer is giving us an error, right? Because it's saying 4 does not equal 2. So all it's saying is that because there's 4 elements in this one array and only 2 rows in this array, we can't do the dot product, right? How are we going to do the dot product if we're missing 2 entire values from this row that would complete it, right? So what can we do to fix this, right? Because we can't just, like, how are we magically going to get more data? This is the data that we collected. So what we can do is do something nifty called transpose the matrix, right? So if we transpose this matrix, we rewrite it by flipping the columns and the rows. So we can rewrite this, and we can transpose it, right? So this would be a transpose matrix of this, and it would look like this, right? So it would be 0.5, negative 1.5, 2, and 1. Oh, doesn't go low enough. Scroll down 2. And then we have 2, negative 1, 0, and 1.5. So we went from this array with 2 rows and 4 columns to this array with 2 columns and 4 rows. So when we dot this with our original inputs array, 2, and I think the last one was 3. Alright, so when we do this, now we can actually start doing it. Alright, so when taking the dot product of 2 one-dimensional arrays, right, we get a scalar output, which means that we get a number like 31 or negative 3 or 5 or 6. We get some number, right, not an array as an output. But when we're doing the dot product with a 2D array or a matrix into a 1D array, we'll be getting more than one output, right? Because we'll have to take the dot product of this row into every single column. and there is obviously more than one column, right? So for this case, we'll be getting two outputs because it's dependent on the columns. So we'll be getting an output for this. That'll be the first value in our array, and the output for this, which will be the second value in our array. And if we had 4, 5, 6, 7, our array would just keep getting bigger and bigger and bigger and bigger. Alright, so why don't we go ahead and plug and chug these numbers to get our A and B values, right? So we can go ahead and pull up the calculator. That's gonna work already, but so let's go ahead and start by solving for A, which was gonna be the first column dotted into this 1D array right here. So we have 0 times 0.5, which is 0, negative 1 times 1.5, which is just 1.5. The negatives cancel, plus 2 times 2, which is 4, plus 3 times 1, which is 3. So our output for A is 8.5. Let's go ahead and solve for B. So now we have 2 times 0, which is 0. Negative 1 times 1, negative 1, which is just 1. 0 times 2, which is 0. Plus 3 times, 1 plus, what are the parentheses here? No parentheses? Alright, we'll just do that later. 3 times 3 times 1.5. Oh, nah, man, I don't know how to use this, I guess. 3 times 1.5. Okay, 4.5. It's a good number. Plus 1. There we go. Okay, so 5.5, 5.5. That is our output. So if we dot these two this transpose matrix to this 1D array, we get this as our output. And you might be asking, like, what does transposing really do? Does it ever change our outcome? Will it ever change, like, the relationship? And most of the time, the answer is no, because the computer is determining what these relationships are, right? So if you just transposed it, somewhere in that matrix, there will still be some sort of numerical relationship between the data. There will be some way for the computer to trial and error bulk its way through and figure out some of the connections. The only situation in which it would negatively affect the outcome is if it got rid of the relationships entirely, right? And I think it's very rare for that to happen, and I don't think it's all too common, so we don't have to worry about it too much. But main takeaway from that little spiel was that you have to understand correlations between the data if you want it to work in the machine learning. If you wanted to work with neural networks and machine learning, right? So yeah, that's pretty much it for how transposing and how matrix dot products works. So why don't we go ahead and go back into the code and then try solving this problem we got, right? So we solved it just now using math, right? By transposing this matrix right here. So we can go ahead and just do that in Python as well, because there is a NumPy function to transpose stuff. And it is, you just take a NumPy array. So if we were to make an array, NP array of inputs, and so you just take this array, this NumPy array, and you transpose it by doing a .t at the end. That's it. And it will transpose that entire matrix for you. And since we've already turned this into these two into NumPy arrays, we can just go ahead and transpose the 2D layer that we saw. So this is what we were looking at when doing the math. This and this. We can go ahead and transpose the weights layer like we did in the math, and then run the code again. So we get 11.5 and 7.5. Okay, so and we get 11.5 and 7.5. Okay, so those numbers don't really match what we got earlier, right? They don't match 8.5 and 5.5. Well, they don't do that because we also added a bias layer, right? We added the bias layer. So what that pretty much did is take our 8.5 and 5.5 and add this array of 3, 2 into it, right? So that's pretty much taking this and adding 3, 2. And whenever you're adding arrays like this, you can just add by index. So index 1 plus index 1, index 2 plus index 2. So we get 8.5 plus, oh, that's a bad 5. That is a very bad 5. Plus 3, and then 5.5 plus 2. And this is going to be our final array. You're still going to get an array as an output, but the array will be a sum of both those two earlier arrays that we saw. So this would be our final output if you included the weights, which is what the computer's getting. So we did everything correctly. So everything looks good for now, and yeah, that's pretty much it. So we went from that big, really super clunky output equation, right, to this tiny, concise uh, dot product function for our output, and we can now, right, treat this output, which is an array of 11.5, 7.5, right? We could treat this as an out or an input for another array. Not sorry, excuse me, not another array, another layer. So this output will then become the input for another layer, and so on and so forth. So that's pretty much it, I guess. Uh, so that was pretty much programming the math that we learned in the last video into Python. We went over some different Python concepts. We also went over some new math concepts such as matrix dot products and what transposing is. And we pretty much created an output equation for a single hidden layer that is concise and easy to read and pretty well thought out. So that is what we did today. Next video we'll be taking a look at turning all of this code right here into object-oriented programming. Well, technically all of it into object-oriented programming. So we'll also be going over some new concepts such as activation functions